Hello, good morning. My name is Abu Nasser Masood, and I am from Mälardalen University in Sweden. So today I'm going to talk about how we can compute weak control closure in a fast and incremental way. So weak control closure captures certain forms of program dependencies. So let's start a bit with the context of program dependencies. Usually we represent programs as control flow graphs, and then in many applications of static analysis such as program slicing, program optimization, debugging, or information flow control, they require to compute control and data dependencies. So data dependencies captures the direct dependencies in the program. If one program is data dependent on one statement is data dependent on another statement, it means that the first statement is using a program variable defined by the second one. For example, in this program, statement 4 is data dependent on statement 1 and 3 because 4 is using the program variable x defined at statement 1 and 3. Another form of dependency is called control dependency that captures indirect control dependencies. So in this case, one statement is control dependent on another statement if second statement decides whether statement 1 can be executed or not. So statement 2 here in this case controls the execution of 3. So 3 is control dependent on the statement 2. So usually, this kind of data dependencies and control dependencies we encode into a graph called program dependency graph. In this graph, nodes are the nodes of control flow graphs, and edges represent either data or control dependencies. And slicing is one application of this kind of data dependencies and control dependencies. So the problem is you are given a program P with a slicing criterion C, and the slicing problem asks to select a part of the statement that affects the execution in C. So C is usually a subset of control flow graph nodes, or more sophisticated slicing criterion can be a set of nodes that are at specific program points. So once we have these data and control dependencies, if we can pre-compute it, then we can formulate the static backward program slicing by a fixed-point computation approach with these two sequence of instructions, two sequence of equations. So it says that given a slicing criterion C, initially the backward slice contains only C. Then in every successive iterations, we compute more and more the control and data dependencies and include them in the backward slice. So this equations at starting point, they reach a fixed point because the set of control flow graphs are finite. To give you an example, for example, suppose we would like to slice this program with respect to statement 4. So initially our backward slice will contain statement 4, and then as we proceed in the successive iterations of this of the fixed point computation, so we traverse the program dependency graph from the nodes in C in the backward directions. So in the next iteration from 4 we can reach 1 and 3, so we will include them in the backward slice. And after some point, we'll reach a fixed point that will include all the nodes that are traversed in this way. So now you see this computation of static backward slice depends on computing the control dependencies. And the standard definition for control dependency was provided several decades before by Frentz and his colleagues in 1987. And this definition says that a control flow graph node M is control dependent on another control flow graph node N if there are two conditions that are satisfied. The first condition is that M must post dominate node N. What does it mean? It means all the paths that start from any node between N and M to the N node must go through M. So this is the first condition. And the second condition says that M does not strictly post dominate N, which means that there exists a path from N to the N node without going through M. The problem with this definition is that this requires that the control flow graph must have a unique exit point. That means the program must terminate. But we have modern programs, for example, reactive systems, distributed systems, web services. These kind of programs do not terminate at all.
So if we do not have any exit point, how can we compute control dependencies from this kind of programs, and how can we for example, compute program slicing? So this is a problem. Another problem is this definition is very much intra-procedural. Okay, there are extensions to this definition that try to handle inter-procedural programs, but the result is very, very approximate. So it was not very effective in practice. And to overcome these limitations, Danisek and his colleagues in 2011, they have introduced the concept of weak and strong control closures. They capture certain forms of control dependencies, specifically non-termination insensitive and non-termination sensitive control dependencies. So, what is weak control closures? Let me give you an example before I go into the definition. So, for example, suppose we are given a set V of control flow graph nodes that includes the start node, node N2 and node N3. Okay, so if we look into the node N1, we see that there are two paths from N1 to node N2 and N3. And these two paths, they end at a node in V, and no other nodes in between are from the V. So we call such paths as V paths, and these two paths are disjoint. So basically that means N1 controls the execution of either N2 or N3. So there is a control dependency here that we should include it. Since there is a control dependency here from node N1 to the nodes in V, which is not included in V, so V is not weakly control closed, and the weak control closure of V must include such node. So that's the definition that is that I have described here. So given any set B, if the set B is weakly control closed, it must satisfy these conditions here, which says that for all the nodes that are not in B, if N is reachable from B, and all V paths from N must end at a unique node. If these two conditions are satisfied, then, for example, we will not have a node like N on here. And that means then the set B is weakly control closed. And this weak control closure captures non-termination insensitive control dependencies, which means that your program might be non-terminating, but this definition assumes that all non-terminating program will eventually terminate. So if we want to capture termination sensitive control dependencies, then we will have to consider the strong control closures, which is not the topic of today. So I will skip it. And another thing is that, for example, this definition, you see that it does not require assuming an end node in the control flow graph. So it is also applicable for all those programs that are non-terminating. So now, in order to compute this weak control closure, we know that if something violates condition 2, then it implies that there must exist two disjoint V paths in the control flow graph, and from some node N. And if we have such node N, which is called weakly deciding, then we can take all those nodes that are reachable from V, we can include all such nodes in the weak control closure of V. So the computation of a weak control closure of a set of nodes V reduces to the computation of the weakly deciding vertices. Now, if we replace, for example, control dependencies by the weak control closure here, so the slicing approach will be able to slice a non-terminating programs as well. But you see that in these equations, the weak control closure will be computed again and again. So we desire that this computation must be efficient. The original algorithm provided by Danisek was had the cubic or space time complexities. So I provided an algorithm in 2020 that has the quadratic or space execution time complexity. In this talk, the approach that I will show, it also has quadratic or space execution time complexity, but the practical efficiency is much better than the earlier one. Probably because the amortized complexity is much better in this approach. So how can I compute such weak control closure that is incremental and fast? So the basic idea is that I would like to transform the control flow graph to a so-called influencer graph. So the influencer graph, it incorporates the influences of all core nodes and join nodes to other nodes in the control flow graph. So core nodes are those nodes that has multiple successors that splits the execution to multiple branches, and join nodes basically merges multiple branches, which has multiple predecessors. So this influencer graph that keeps track of these branch levels to find the disjoint paths. So this is one benefit. Another benefit is that it is easier to find V paths in this at the influencer graph level. Once we have this influencer graph, then we do some simple data flow analysis to compute the weak control closure of V. And the idea is that the approach is also incremental, which means that in the latter field, if we need to compute the weak control closure of a set V1, which is a superset of V, we only need to compute for perform the data flow analysis for all those nodes that are in V1 but not in V. So in this way, the approach is incremental. Now, how can we build an influencer graph? So suppose we are given this control flow graph. The idea is that we traverse this control flow graph paths. So the path that will start from core node or join node, or from the start node, and a path will end also at a core node or join node, or to the end node of the control flow graph. And no other node in between a path can be core node or join node. So that's the idea. So suppose we start from N0 to N1, we must stop this path at N1 because N1 is a core node here. And since N0 is not a core or join node, there is no influences here to encode here. So in the influencer graph, we will have nodes but no edges in this case. Then we move on. We are considering the path N1 to N11. This path must end here because N11 is the stop node. And we see that it is in the, suppose we assume that this path is in the false branch of N1. So, and N1 influences the execution of N2 and N11 that we encode here in this graph here. But we also attach edge levels. For example, by F, we mean that these nodes are in the false branch of N1. And we also include the distances from, for example, N2 to N1 here. These distances will help us find the minimum V paths later. Okay, so we continue like this, for example. So then in the next we consider the path N1 to N3. This is in the true branch. We encode the branch levels here. We go on in this way. And at some point, for example, we can also have paths from join nodes. And join nodes does not have true or false branch. So we consider a default branch, for example, D, with the distance we encode like this. We move on, and at some point, for example, in this case, node N10 is interesting because N10 can be reached from N6 by following either true branch or false branch. So we input TF here as a new branch levels. And eventually, we've traversed all the paths and build this influencer graph. That requires traversing all the nodes in the control flow graph exactly once. So this approach is efficient. Once we have this influencer graph, it has certain properties. For example, the first property says that any path N to M in the influencer graph implies that there exists a control flow graph path from M to N. First property. And second property says that any V path M to N in the control flow graph implies that there exists a path from N to M in the influencer graph, and no other node in this path is from V except N. So if you think like, for example, node 11 is in the state V, so N1 to N11 is a V path, and if you look into the influencer graph, there is an edge from N11 to N1, and N1 is not in V. So we will use this property later. And the third condition says that if there exist two V paths that coincide at the same node, but probably they have different distances, we prefer the one that has the minimum distance. So these three properties will guide us in our data flow analysis. And the data flow analysis is very simple. It contains three pieces of information. So the domain is the set of nodes times the set of integers times the set of edge levels. Bottom is here just for the initialization purposes. And the set of nodes, basically, we consider these nodes to encode the end node of V path. Okay, and Z is to consider the distance of a node from its V path, from the end node of V path, and edge levels are there to find the disjoint branches.
And once we have this domain, then we can do some, for example, calculation, like how do we compute the data flow values at each particular node n. We have some auxiliary functions here. So xn, the idea of xn here is that it looks into the predecessor nodes in an influencer graph, predecessor nodes of n, and see what are the n nodes, n node of v paths. So it collects all those n nodes into xn. Yn collects all the edge levels from n to its predecessor nodes, and Zn computes the minimum distance from n to the v paths. So once we have these auxiliary functions, then we can use this data flow analysis, these equations to compute the data flow values. So it consists of four equations. The first equation, the condition says that xn greater than 1 and yn greater than 1. It implies that from node n, there exist two disjoint v paths. That's yn greater than 1 means they are at two disjoint, they are at two, for example, disjoint branches, and xn greater than 1 implies that they end at two different end elements of v. If this is the case, what we do is basically we consider n as a new element in the v set v. So we update an into n0 and bottom. So n0 means n is now the trivial n path with distance 0. And once we have this value, an will never be changed later. The second equation says that two paths ended with different v elements, they overlap. For example, if you consider two paths n2 to n1 and n11 to n1, they are in the same branch f. So, and it means that this path basically overlaps, and in this case we consider we update an by that n node in the set v that has the minimum distance. Basically, the minimum distance we have computed in the in Zn. So that's the idea. The third equation says that two v paths end at the same node. For example, if you look into this paths from n4 to n3 and n4 to n3 via n7, they have different distances. So, and as I said, we prefer the one that has the minimum distance. So in this case, we encode the v path into the set an that has the minimum distance. And the final one says that it simply extends the v path. So if we have a v path from, for example, n6 to n10, and when we are at n5, we say that okay, the v path is from n5 to n10 with the updated distances. That's all. So this is how we update the data flow values, and eventually we reach a fixed point. When we reach a fixed point, all the nodes for which a of n is, for example, n0 bottom, and if n is not in v, then n are weakly deciding vertices. And those vertices basically helps us compute the weak control closure sets. Now, how can we compute it incrementally? Suppose we had analyzed this graph when our v includes only node n4. All these states are due to initializations, but since we have node n4, we start with n4 0 bottom, implying that n4 is the trivial n path, and then the data flow analysis basically moves forward and updates the values according to the data flow equations. And now in the next, for iteration, suppose our v includes a new node n7, we do not need to discard all those values. They are there. We just need to say that now we have a node n7, we update the value of n7 by n70, and this will affect all the data flow values at all nodes that we can reach by forward traversing of this influencer graph. So in this case, it only updates the data flow values here, here, and here. So that's how the analysis is done incrementally. And that's why it is, even though the worst case execution time is quadratic, it is still very fast. So I implemented this algorithm in the Clang LLVM frameworks, and the algorithm that was developed in SAS20 that is also implemented in the same framework. And I did some experiments by selecting benchmarks from SPECCPU 2017, and I took 7 benchmarks because all these 7 benchmarks are implemented in the C language.
and my implementation can only handle C programs. So if you look into the experimental results, especially the Perl bench and GCC, they are the most they are the largest benchmarks in this benchmark suite, and you see that this new algorithm, it has a speed up, quite a lot. But in other cases, you see the speed up is not that much, so the result is a bit skewed. But that's because each program in Perl bench and DCC, they are quite large. The size of the control flow graph is, for example, approximately 20 or more. So when the control flow graph is larger, we get higher speed up. On the other hand, other benchmarks, their control flow graph is very, very small. So we cannot gain much from there. But this is enough to give us an indication that the approach is very efficient in this case. So what's next? Basically, my idea was, I always had thought that probably I can find an algorithm that is linear or log linear in the worst case to compute WCC. So could not find that algorithm with that complexity, but instead in this work, what I could improve is improving the amortized complexity that gives us the practical efficiencies. And if we can find an efficient algorithm that has some consequences, for example, in my recent work, it says that the computing weak control closure and computing the SSA program has certain form of duality. Like there is an algorithm. If you can use to compute weak control closure, you can use the same algorithm in a dual way to compute the most expensive part of computing SSA programs. And the consequence is that if you can improve this algorithm, it will improve the program slicing, improve the algorithm to compute non-interference. Also, SSA programs are used to compute data dependencies. So all these algorithms will be improved. So anyway, the practical efficiency of this algorithm is much better than the earlier one. So we can say that this is the best baseline approach from now on. And I think that's all from me that I wanted to say. Thank you.
Thanks. This was for the weak control closure, right?
Yes.
So what's the gap for doing something similar for the strong control closure?
Sorry, what's that?
What's the gap for the strong control closure?
Okay. The gap is okay. So the computing strong control closure is force case complexity is always 1 degree higher. So if, for example, this is quadratic, computing SCC will be cubic. This is one thing. And strong control closure, let me give just to say that here, for example, suppose you have an edge from here to some nodes that diverge, that is non-terminating. So the weak control, that means either from here, from a node here, either we can reach a P node or the computation can diverge. So there is a dependency from this node to the set of B when we consider non-termination. So a strong control closure must include such node. That node is not captured by weak control closure. So that's why we need a strong control closure to compute slices, for example, when you need verification of non-terminating programs. So that's the difference.
Okay, thanks.
Yeah, thanks very much for the nice work. I missed the first part, but it's quite exciting. So here, the incremental is in the sense that each iteration, there's some incremental update. I wonder, do you see the application for maybe you have two versions and you have slightly code changes? Do you see how this already happens?
Can you repeat the last part?
Yeah, my question is, in reality, very often your software evolves, right? You make little changes. So now do you foresee maybe you can adapt this algorithm to handle two versions of code? They are fairly similar in terms of control flow graph.
Okay,
If the software evolves, means the control flow graph changes as well. So basically, in this work, I assume the control flow graph is not changing. But if the control flow graph changes, we need to identify the changes and we need to reanalyze only those parts that has changed. So yeah, in this way, it can be incremental in this way as well.
Okay, cool. Thanks.
Any other questions? Last chance. Okay, if there are no further questions, that's